We will quickly simplify this electrical network and find the power delivered by each of the energy source in that given network. Now what we can see here is we have three energy sources, two current sources and one voltage source. Now if we focus on this part of the circuit, we can see here with this current source we have a resistor that is connected in parallel with that current source. So we can easily transform this current source to an equivalent voltage source, and with that equivalent voltage source this resistor will be connected in series. Similarly, in this part of the circuit again we have a current source, and with this resistor is connected in parallel. So again we can easily transform this current source into an equivalent voltage source, and with that voltage source this resistor will be connected in series. And now if we can visualize that equivalent circuit, then in that circuit we will have here one voltage source and here one resistor. We will not have any parallel branch here. Again we will have one voltage source here, and with that we will have this resistor connected in series here. And again this parallel branching, or this resistor will not be here connected in parallel. That means after transformation this parallel branch and this parallel branch will not be there in that electrical network. But here we have a voltage source, and with that again this resistor is connected in parallel. So here we will not go for the transformation of the voltage source, rather we will keep them as they are in the original circuit. Now if we analyze this circuit, we will see that here we will have one mesh, here we will have another mesh, and here we will have another mesh. So in total in this electrical network we will be having three loops or three meshes. Now on the other hand, if we identify the nodes in this electrical network, we will see that here we have one node, here we have another node, and here we have another node, but that is not a separate node, because this node, between this node and this node we have no more component connected in between. So this and this node are basically same node. So these two will be considered as our second node in this circuit, and this is our third node. And at the bottom of the circuit we have a common node, and that will be taken as a reference node, means that node will be connected with the ground. So apart from that grounded node or reference node, we have three nodes in that circuit. So if we go for KVL or mesh analysis, we will have three mesh equations. So in those mesh equations we will be having three variables that we need to solve. And if we go for KCL or node analysis, then we will be having again three equations from three nodes, and again we will be having three variables that we need to solve. But we know that the choice of application of KVL or KCL to simplify any electrical network depends on the number of meshes or number of nodes. So whichever is less, we go for that approach. But here we have three meshes and three nodes, so choice is ours. Now since we are here focusing on KCL or node analysis, so here we will form node equations. Now this is our first node that we have marked as A, and corresponding potential we have assumed as VA, V suffix A. Similarly, this is our node B, second node, and this is similar to this node only. And the potential of that node we have assumed as VB. And this is our third node that has been marked as C, and the potential of that node as VC. And this is our reference node. So first we will write the equation for node A. At node A, we have three branches connected. In this branch, we have a current source whose direction is towards the node. So that is an incoming current for that node. But for the other two branches, since the direction of currents are not mentioned, so we will be assuming that the currents are leaving that node, and that is the convention that we follow. With respect to this branch, the potential of this node is VA, and potential of this node is 0, because this is connected with the reference node whose potential is 0 volt, which is grounded. So the current value through this branch will be what? Potential difference between these 2 points or across this resistor divided by the resistance value. And for this branch, the current value through this branch will be potential difference, means VA minus VB here, divided by the resistance value. And we know as per KCL, the algebraic sum of all the incoming currents and outgoing currents with respect to any node is 0. That means summation of all the incoming currents or the currents that are approaching that particular node will be equal to the summation of all the outgoing currents, means the currents which are leaving that node. So here two currents are leaving this node A and one current is approaching that node. So as per KVL, this is the current which is leaving plus this is the current which is leaving, and that summation of that value will be equal to the incoming current which is approaching this node, which is 2. Now if we simplify this equation, then the simplified form of that equation will be this, which we have marked as our first equation. Now if we analyze node B, then we can see here that we have 4 branches connected at node B, and among those 4 branches one is current source, and for other 3 branches direction of currents through those branches are not known, so we will be assuming that those currents are leaving this particular node B, and for this current source, which is the value of that current source is 1 ampere, that current is approaching this node B. So our node equation will be, now for this branch the current value will be the potential difference between these 2 points, which is VB minus VA divided by the resistance value, which is 1 ohm, plus the current value which is again leaving this particular node. As we know, these 2 nodes are same, so here it will be VB minus 0 divided by 3, plus the current value which is flowing through this branch, and that is again leaving, so it will be VB minus VC divided by 1, and that will be equal to the total incoming currents. But here for this node B, the only incoming current is 1 ampere. So summation of these 3 currents will be equal to 1. Now if we simplify this equation further, then that will be, here VC has been replaced by 2. Why? Because the potential difference between these 2 points is VC minus 0. And we also can see in this circuit that this voltage source having voltage value 2 volt is also connected in parallel between these 2 points. So we can say that the potential difference between these 2 points is 2 volt. That means VC is equal to 2 volt. So the simplified equation will be this. Now if we solve these 2 equations, then we will be getting the values of these 2 variables VA and VB, and these are their values. Now power delivered by 2 ampere current source will be 2 into 3.07 watt, and that is 6.14 watt. Now why 2 into 3.07? Because the current value of this current source is 2 ampere, and the voltage drop across this current source is VA, and that we have obtained as 3.07 volt. So power loss, we know power loss or power delivered is voltage multiplied by the current value. So current value is 2 ampere and voltage difference with 3.07. So power delivered by that current source will be 6.14. Similarly, power delivered by 1 ampere source will be 1 into 2.6. Why 1 into 2.6? Because the current value of this current source is 1 ampere, and the voltage drop between these 2 points or across this current source is VB minus 0, so VB, and the value of VB we have calculated as 2.6 volt. That means power delivered by that 1 ampere source will be 2.6 watt. The total power delivered by those 2 current sources will be 8.74 watt. Now in the circuit we have another source, which is voltage source. So for that we need to find the current value will be flowing through this voltage source, and then from there we can calculate the power delivered or power absorbed by that energy source. To do that, we will be analyzing for node C, and here we can see that we have three branches which are connected with node C. And for these 2 branches, the current directions are not known. So we will be assuming that currents are leaving. And since this is a voltage source and this is the positive terminal and this is the negative terminal of the voltage source, we know that the current leaves the positive terminal of the voltage source. So if we assume that the current value in this branch is I, so the direction of that current I will be assuming as towards that node. So here at node C, the current equations will be the current value through this branch plus current value through this branch will be equal to the current value through this branch. So here the value of VC we know that is 2 volt that we have already seen, and the value of VB is 2.6 volt that we have already calculated. So if we simplify this equation, then the value of current will be minus 0.1 ampere. That means actually this current is flowing in opposite to our assumption. That means the current is actually flowing in this direction through this 2 volt voltage source. So actually here power will be absorbed by this 2 volt voltage source, and that value will be the voltage value which is 2 and the current value which is 0.1, and the total power absorption here will be 0.2 watt. So this is the total power delivered and power absorbed by all these energy sources. I hope this class was meaningful for you. Thank you.